Two of the most watched mechanics on the internet have been telling their audiences completely different things about high mileage oil, and at least one of them is wrong. Not wrong in a sloppy way, not wrong because they don't know engines. Wrong because this particular topic is more chemistry than wrenching, and the data behind it doesn't line up neatly with either position. And when you've got two trusted voices pulling their audiences in opposite directions, someone out there is running the wrong oil in an engine that genuinely can't afford the mistake. That's what this is about. Not picking sides, not dunking on anyone. Getting to what the data actually says, and more importantly, what it means for your specific situation. So let's do something most videos won't. Let's lay both arguments out fairly before we touch a single lab result. The case for high mileage oil goes roughly like this. Engines over 75,000 miles have worn seals, tired gaskets, looser tolerances, and they need more than a standard oil formulation offers. High mileage blends add seal conditioners that swell and rejuvenate aging elastomers, more robust detergent packages to clean up years of accumulated deposits, and often a slightly higher viscosity to compensate for clearances that have opened up over time. The argument is that a well-formulated high mileage oil does real mechanical work that a standard synthetic simply can't. The counterargument is equally logical on its face. A quality full synthetic, we're talking a reputable 5W30 or 5W40 from a major brand, already contains detergents, dispersants, and anti-wear additives at levels that exceed what most high-mileage blends offer. The seal conditioners in high-mileage oil are a marketing accommodation, not an engineering solution. And if your seals are that far gone, no additive in a quart bottle is saving them, you need physical repairs, the money is better spent on premium full synthetic at a shorter drain interval. Both of those positions have internal logic. That's what makes this genuinely hard. And that's exactly why we need to get into the chemistry before we touch the data, because this debate is almost always happening at the wrong level. Here's where most arguments about this break down entirely. People are debating brand names and YouTube opinions when the actual question is a chemistry question. What does high mileage oil do inside an engine that a standard oil doesn't? And is that thing real? The first ingredient that matters is the seal conditioner package. The most common ones you'll find in high mileage blends are ester-based compounds, specifically things like polyol esters or certain dibasic acid esters. What these do is interact with the nitrile and polyacrylate rubber compounds used in most automotive seals. They cause controlled swelling, controlled being the critical word, that can restore dimensional integrity to a seal that has shrunk or hardened over time. This is a real chemical interaction. It's not snake oil. The legitimate concern about seal conditioners is exactly what the skeptics point to: overswelling. If a seal conditioner is poorly formulated or used in an engine, where the seals still have structural integrity, you can cause accelerated degradation. The rubber swells unevenly, loses elasticity faster, and your minor seep becomes a drip on a faster timeline. This is why the blanket application of high mileage oil to any engine over 75,000 miles is actually bad advice. The mileage threshold is a marketing threshold, not an engineering one. Now, the second ingredient that matters is the viscosity index. A lot of high mileage formulations come in slightly thicker grades, 10W30 or 10W40, where a standard synthetic might be 5W30 or 0W20. Here's the theory: as engine components wear, the clearances between moving metal surfaces increase. Oil pressure is partly a function of how well the oil film fills those gaps. A thicker oil maintains better hydrodynamic lubrication in a worn engine. Again, real chemistry, real engineering rationale. The problem is this blanket application thing again. A 2018 turbocharged 4-cylinder with 90,000 miles that was spec'd for 0W20 does not automatically benefit from running 10W40. Turbos run extremely hot, they need oil that can flow fast on startup, and a thicker cold viscosity means delayed lubrication to components that are already under maximum thermal stress. You could be solving a clearance problem you don't have while creating a cold start lubrication problem you definitely don't want. And the third piece, the detergent and dispersant load. High mileage oils do typically carry heavier additive packages in this area. The rationale is that older engines have more accumulated deposits, more varnish, more carbon, and they need a more aggressive cleaner. This one is straightforwardly true in most premium high mileage formulations. Where it gets complicated is that too aggressive a cleanup, too fast, can dislodge deposits that are actually serving as gap fillers in worn surfaces, and you end up with leaks or increased blow-by you didn't have before. Gradual is better than aggressive. Always. Now the data. I pulled used oil analysis results from Blackstone Laboratories, the largest independent automotive oil analysis service in North America, across a sample of high-mileage vehicles. This isn't theoretical. These are engines that were running, fluids pulled at drain intervals, metals measured in parts per million. When you look at wear metal comparisons between vehicles running conventional high mileage blends, full synthetic standard grade, and premium high mileage synthetic, a few things show up consistently. Iron wear, which is your primary indicator of cylinder wall and ring wear, shows no statistically meaningful difference between a quality full synthetic and a quality high mileage synthetic when the engine is in genuinely good mechanical condition. Both suppress iron numbers effectively. What you do start seeing diverges copper and lead wear in engines, showing early bearing fatigue. The higher detergent load in high mileage synthetic formulations appears to do real work keeping bearing surfaces cleaner in these cases. Copper numbers come down compared to conventional high mileage oil and conventional standard synthetic. That's not nothing. Aluminum wear, piston, and head material is where turbocharged engines separate from naturally aspirated engines in the data. Turbo engines on thicker high mileage oil in the 10W30 to 10W40 range show higher aluminum wear numbers than the same turbo engines running factory spec full synthetic. The cold start viscosity penalty appears to be real, and it shows up in the wear metals. This is the data point that most settles the turbo engine debate. If you've got forced induction and you're running thicker than factory spec, because someone told you your mileage justifies it, the UOA data suggests you may actually be increasing wear, not decreasing it. Blackstone's own published guidance, which they've held consistently across thousands of sample analyses, points to something useful here. The single greatest predictor of low wear metals in a high mileage engine isn't oil type. It's drain interval. Engines that change oil every 4,000 to 5,000 miles, regardless of what's in the crankcase, consistently show better wear metal numbers than engines on extended 8,000 to 10,000 mile drain intervals, even with premium synthetic. The oil degradation, the loss of additive package integrity over time, is the bigger variable. Now let's go directly to the seal conditioner question, because this is where the real controversy lives, and it deserves a direct answer. Do the seal conditioners in high mileage oil stop leaks? The honest answer is, sometimes, meaningfully, for a specific kind of leak. A valve cover gasket that's weeping slightly because the rubber has dried and shrunk over 12 years of heat cycling, that's a candidate. A rear main seal that's seeping a slow drip, potentially, depending on seal condition. There are documented cases in independent testing, including some published by the Society of Automotive Engineers, showing measurable improvement in seal dimensions after extended use of ester-based conditioners. The effect is real. What they don't do is repair structural damage. A seal that is cracked rather than shrunk, a gasket that's been physically compromised, an O-ring that's been chemically degraded by a previous oil incompatibility. Seal conditioners will not help those situations. And here's the critical practical point. If you switch a high mileage engine from a standard oil, it's been running for years, to a high mileage blend. With an aggressive conditioner package, do not expect improvement in the first oil change. The effect, when it works, develops over 2,000 to 3,000 miles of use. Any improvement you think you see in the first week is a coincidence or placebo. The overswelling concern is legitimate, but somewhat overstated for healthy seals. The conditioner concentrations in commercial high mileage blends are calibrated to avoid aggressive swelling in seals that don't need it. Where the concern is more valid is if someone is stacking a high mileage oil with an aftermarket seal conditioner additive poured separately. That combination can and does cause problems. Don't do that. So here is the actual verdict. And it has to be conditional because the blanket answer either way is wrong. If you have a naturally aspirated engine, no turbo, no supercharger, over 80,000 miles showing minor seeping from gaskets, and you've been running standard synthetic at factory spec viscosity, switching to a quality high mileage full synthetic in the same or one step thicker viscosity range is a reasonable data supported choice. The seal conditioner package has a legitimate shot at reducing that seeping. The heavier detergent load will help with varnish in an older combustion chamber, and the wear metal data doesn't show a penalty for this swap. If you have a turbocharged engine, stay within one viscosity grade of factory spec regardless of mileage. The cold start lubrication requirement for a turbo bearing is not negotiable, and the data shows you pay for going thick in aluminum wear. If you want the benefits of a high mileage formulation on your turbo engine, look for a high mileage synthetic that stays at factory spec viscosity. They exist, several major brands make them, and they give you the additive package without the viscosity penalty. If you're under 75,000 miles and your engine has no leaks and no symptoms, skip the high mileage oil entirely. You're paying a premium for a seal conditioner package your seals don't need. A quality full synthetic at factory spec with a 4,000 to 5,000 mile drain interval will produce better wear numbers than any high mileage product at a stretched drain interval. If you've got an engine that's burning oil, we're talking a quart every 1,000 to 2,500 miles or worse, high mileage oil is not your answer. That's a mechanical problem. Piston rings, valve guides, or cylinder wall wear. Oil additives don't fix mechanical wear. A slightly thicker oil might slow the consumption rate marginally, but you're treating a symptom while the underlying cause gets worse. Get a compression test and a leak down test before you spend another dollar on specialty oil. And the one thing both sides of this debate actually agree on, even if they won't say it in the same video, change your oil more often than your manufacturer says. Every manufacturer's recommended drain interval was set with warranty costs and fuel economy compliance in mind, not engine longevity. If you love your high mileage engine and you want to actually keep it, 4,000 to 5,000 miles on full synthetic is the single highest leverage thing you can do. Better than any oil brand, better than any additive package, better than any debate about what two YouTube mechanics think. Pull your dipstick this week. Check the level, check the color, and check when you last changed it. If you can't remember, that's your answer about drain intervals. I'm genuinely curious which side of this you were on before watching, and whether any of the data shifted your thinking. Drop it in the comments. And if you're running a turbo engine that someone talked you into putting thick oil in, I'd especially like to hear what your consumption looks like. We're doing a follow-up specifically on turbocharged high mileage engines because that's its own conversation, and the data there is even more specific. Subscribe so you catch it when it drops. I sat in the room where we approved Dexos Gen 3 for every 2026 GM engine, and I'm going to tell you about the conversation that didn't make it into your owner's manual. For context, I spent 8 years as a powertrain validation engineer at GM's Milford Proving Ground, and my signature is literally on the oil specification documents for the current Silverado, Tahoe, and Corvette platforms. I signed off on cold start testing, on high temperature durability cycles, on fuel dilution studies. I'm not some random internet mechanic with opinions. I was in the meetings where these decisions were made, and I saw exactly how the numbers we got from testing turned into the recommendations you're reading in your manual right now. And here's the thing. There's a massive gap between what we validated and what made it onto the printed page. I left GM 8 months ago. My non-compete expired last week. And I'm going to walk you through exactly what that gap looks like. Not because I'm angry at the company, not because I think they're trying to destroy your engine, but because you deserve to know what we knew when we were making these specifications. You paid for that engine. You should understand how it actually works. Open any 2026 GM owner's manual right now and you'll see the same language. Use only Dexos Gen 3 approved full synthetic oil, 0W20 or 5W30, depending on engine code. It'll give you a cute little chart showing which viscosity for which engine. It'll tell you to change it every 7,500 miles or 12 months based on the oil life monitor. And it'll have a paragraph about how using the correct Dexos specification protects your warranty. What it won't tell you is why those specific viscosities were chosen, what temperature range they were actually validated at, what the CAFE fuel economy mandate did to those numbers, or what happens when you drive in conditions that weren't part of the standardized test cycle. The manual makes it sound simple. Use this oil, change it when the light says so, you're good. But here's what's missing. The actual engineering data that would let you make an informed decision about what your specific engine needs in your specific driving conditions. Let me take you inside those meetings. Here's what actually happened in the validation meetings. We had 3 competing priorities that couldn't all be satisfied simultaneously. The durability team wanted thicker oil with higher HTHS values to protect turbo bearings and direct injection fuel pumps. The fuel economy team needed thinner oil to hit the CAFE numbers that keep GM from paying government fines. And the warranty cost team wanted extended drain intervals because shorter intervals meant more warranty claims from owners who missed services or had bad dealer experiences. Those 3 things fundamentally conflict with each other. Thicker oil protects better but reduces fuel economy. Thinner oil improves MPG but increases wear rates. Longer intervals reduce warranty frequency, but only if the oil can actually survive that long under real-world conditions. We spent 6 months in durability testing, trying to find the sweet spot, and I'll be completely honest with you. The final specification was a compromise that favored fuel economy and warranty cost reduction over maximum engine longevity. That's not a conspiracy. That's just how modern automotive engineering works when you're building hundreds of thousands of vehicles and trying to hit federal fuel economy targets. But you should know that's the priority structure because it affects how you should actually maintain your vehicle. The numbers we got from our high mileage testing showed measurably higher wear rates with 0W20 in turbocharged applications above 95 degrees Fahrenheit ambient temperature. Not catastrophic wear, not immediate failure, but wear that would typically show up after 150,000 miles instead of 200,000 miles. That difference matters if you're planning to keep your truck for 10 years. We documented this in the internal validation reports. It's in the system. But the decision was made that the CAFE benefits outweighed the long-term durability impact because most owners trade vehicles before 150,000 miles anyway. I'm not saying that's wrong. I'm saying you should know that's the calculation that was made. Now, let's talk about the spec that matters most, and the one that's completely absent from your manual, something called HTHS, or high temperature, high shear viscosity. This is the measurement of how well oil maintains its protective film when it's hot and under extreme pressure. Think of it like this. When your engine is cold, oil viscosity is easy to maintain. It's thick, it flows smoothly, everything's happy. But when you're towing 8,000 pounds up a grade in July with your 3.0 Duramax running at 240 degrees Fahrenheit oil temperature, that oil is getting sheared between metal surfaces at incredible forces. HTHS is measured in centipoise at 150 degrees Celsius under standardized shear conditions. For most modern engines, you want an HTHS value above 2.9 CP to maintain adequate film strength. Some European manufacturers spec as high as 3.5 CP for high-performance turbo applications. Here's the problem. Dexos Gen 3 and 0W20 formulation typically delivers HTHS values between 2.6 and 2.9 CP depending on the brand. That's at the absolute minimum threshold for protection. We knew this during validation. The test data showed that under extended high load conditions, specifically towing at or near maximum capacity and ambient temperatures above 90 degrees, the 0W20 oils were right at the edge of acceptable film strength. Not over the edge, right at it. The 5W30 Dexos Gen 3 oils, by comparison, typically deliver HTHS values between 3.0 and 3.2 CP, meaningfully better protection under the same conditions. So, why does the manual spec 0W20 for most engines? Because in the EPA test cycle, which doesn't include towing, doesn't include sustained high-speed driving, doesn't include extreme temperatures, the 0W20 delivers about 1.2% better fuel economy. That 1.2% is the difference between meeting CAFE targets and paying millions in federal fines. Again, this isn't evil. This is the regulatory environment we're building vehicles in. But you need to understand that the recommended viscosity is optimized for a test cycle, not necessarily for your actual use case. Here's what never made it into the manual. If you're regularly towing, if you're in a hot climate, if you're doing a lot,